Yin-Che tell us about quantum Hall effect. Just before I forget, I will try to remember at the end of the lecture, but in case I forget, if you have the white envelope with the receipt, please go hand it back to Jandira before you go eat during the coffee break. So right after class. Was it clear? So some people still have the white envelope with the receipt. You need to return it with the receipt signed. So that's crucial that you do it right after the class. Okay, so it's a pleasure to learn about quantum Hall from Yin-Che.
All right, so I think we can start. First of all, I would like to thank Pedro for inviting me to this wonderful place. And the lectures I'm going to deliver is about quantum Hall effect. And it's actually a huge subject, so then this lecture is really just a brief introduction, give you some idea about what quantum Hall effect is and what's the physical mechanism behind it. There are way more topics related to quantum Hall that I'm not able to cover. So to understand what quantum Hall is, it would be good to just start by reminding ourselves what is the classical Hall effect that we learned in high school. So the Hall effect just happens in the context that, let's say you consider a two-dimensional plane, and you have electrons moving on a two-dimensional plane, and you apply a magnetic field that is perpendicular to the plane. Okay. And then the upshot for the quantum Hall effect is that the upshot for the Hall effect is that the magnetic field, the B field, will introduce Lorentz force that we learned in high school. And the Lorentz force and the consequence of Lorentz force is that the system will have some resistance that is a transverse, we call it Hall resistance or transverse resistance that I will explain in a minute. So, that is what Hall effect is. So let's say the concrete setup is that, let's say we want the system to have a current that, let's say, along the x directions. This Jx is my current density. And to achieve that goal, what I need to do in the end is that I need to apply an electric field perpendicular in the y direction in order to compensate the Lorentz force, right? That is something we learned in high school. So we can try to be more concrete about this physics. Let's say we have this current density, and then the current density can be written as the density of the carriers that is the electrons that can carry the current in the system that I will call N, and then times the electric charge, and then times the velocity of the electrons that I call Vx, right? And then what we know is on each electron, there will be a Lorentz force, right? As well as a force come from the electric field, right? And the force will be minus E times Ey and plus my Lorentz force, right? So, Vx times B. And then in order to have this current, then what we need is that this Lorentz force goes to 0, right? This gives me a relation that is my electric field should equals to Vx times B, that is minus Jx over N times E, and then multiplied by magnetic field strength, right? That is what we know from high school. And then what we can do is to compute the so-called Hall resistance, which in general we can define the resistivity as a tensor or a matrix that takes value that I will call rho mu nu, and with the mu and nu take value as x and y. That's really just my directions on the plane, right? So then we will have this Ohm's law that is my electric field will be equals to my resistivity tensor times the current density, right? With this relation, what we will end up with is this Hall resistance, which is an antisymmetric if you exchange the x, y, and it will be B over n times E, right? That is what we learned from high school. By the way, so feel free to interrupt me at any point, ask any questions you would like. Okay, so that is the Hall resistivity that in a classical world, right? So we can draw a plot. So the thing you would notice is that the resistivity is really proportional to the strength of my magnetic field, right? And we can draw a plot that is on my x-axis, I have my field strength, and on the y-axis is the Hall resistivity, right? And then from this, we know that classically, what you should expect is really just a straight line that has it equals to, the resistivity equals to, the slope is B over n times E. That is the classical story. You can also work a little bit harder to get the transverse, the longitudinal resistivity like rho xx, and what you will find is actually it just stays as a constant that is independent of the magnetic field, right? That is the classical story. And as we learned in quantum mechanics, we know that many like classical phenomenon will break down in the quantum world. That's also the case for this Hall effect. So the thing is, if you lower the temperature of the system if you make the temperature low enough, and you look at a region that has very strong magnetic field, typically around 5 to 10 Tesla and then what you will find is that this Hall resistivity starts to develop the so-called plateaus. That is, do I have some other colors? So you will start to say that my Hall resistivity starts to form a pattern like this. So I will say the quantized plateaus of the Hall resistivity rho xy, and there are multiple plateaus of this Hall resistivity. And more remarkably, the Hall resistivity at each plateaus actually takes a quantized value that is rho xy equals to 2 pi h bar over E square and times 1 of nu. And this nu is what we usually call filling factor, and nu equals to integer. So that means for those plateaus that I draw here, you will have the first plateau to equals to mu equal to 1, and the second equals to mu equal to 2, and it keeps on going. So that is what we called quantum Hall effect, and it was that is what we called integer quantum Hall effect, which was originally discovered by von Kleisen in 1980. And of course, he got a Nobel Prize for this remarkable discovery. And this quantity, so you can say that the Hall resistivity at those quantum Hall effect is really, first of all, it's independent of the magnetic field, right? And it's a combination of two physical constants. One is the Planck constant, the other is the electric charge. And indeed, experimentally, people can achieve really accurate measurement for this Hall resistivity. So I can, for example, this constant is also called a Kleisen constant. And experimentally, people can really measure it to extraordinary accuracy, which I will write it down to showcase that how accurate people this experimentally this number can go to. So you say there are many digits that people can experimentally can measure just for this phenomenon, and indeed that's one of the most precise physical quantity that we human beings can measure. And for a while, I think this method was used to determine the values of Planck constant. But I think, if I remember correctly, nowadays there's another way to give you a more precise evaluation of Planck constant, and this Hall resistance becomes the canonical way for people to measure the physical constant, this electric charge. So this is really a remarkable phenomenon in quantum matter physics. And one important thing is here, this quantum phenomenon happens in the macroscopic level, not in the microscopic level, like what we learned in quantum mechanics, that if you consider a single atom, you may say the levels of the energies gets quantized. But here, it's a phenomenon that come out of many electrons in the system, and eventually the quantity you can measure is also a macroscopic quantity. It's this resistance written here. So,
sorry, can I ask a question?
Yeah.
So to define rho xy,
yeah,
so first you tune the electric field to make sure the current is just in the x direction, right?
Yeah.
And so that gave a precise way of fixing the electric field, and then the current is in the x direction, then you determine rho xy.
Yeah.
From this point of view, I'm not sure I understand what's the definition of rho xx. Rho xx is 0 right now, right?
Yeah, in this definition.
So what's the definition that gives the constant?
You need to work a little bit harder, like consider the so-called Joule formula and so on to derive the rho xx. So you know the rho xx comes from the scatterings of your electrons with impurities and so on. You need to include that to properly define it.
Okay.
Yeah, you can. So yeah, for you, if you're interested in how to get the entire things like rho xx, you can check the Daviton's lecture notes. In his lecture notes, he has explained the full story in the classical world.
So right now, naively, there was no rho xx, right? Because
right.
you explained that there's only EY and B.
Yeah.
But you are saying there exists electric field in the x direction if we are more careful, but it's small? Or it doesn't exist and you need a slightly different definition?
You need a different mechanism to get rho xx. Right. Yeah. I think there's a question. Yeah. I'm not sure if I understand the question. I guess probably it's too far away. I cannot
Yeah, so I can
hear.
pass the microphone, but it's about why there is no B in row XY.
Okay, that's something I will explain. That's the main task for this lecture, to understand why do we get this remarkable quantization of the Hall resistance independent of magnetic field. Yeah.
But shouldn't it approach the line when, like, you take the limit as h bar goes to 0? Because, like,
But h bar is not.
No, repeat the
The
question.
question is, if I, yeah.
you should get the classical limit if you set h bar to 0.
Well, that's probably the remarkable point of this, right? Yeah. So that's probably the remarkable point of this, right? So it's a quantum phenomenon that happens macroscopically. You cannot really take h bar goes to 0 to recover the classical physics.
Okay, so
Yeah.
it's a separate phenomenon. It's not like you can't derive the classical Hall effect from this quantum Hall effect.
Right. Yeah, it's different. Yeah. So, any other questions? Yeah. So the other thing I would like to mention is for those.
There's one more question there.
Okay. Yeah.
Listening to his question at the beginning, you said that this only works for low temperatures.
Yeah.
So could we get like something like the classical regime via the thermodynamic limit? Like using the thermodynamic limit?
Yeah. Can you repeat the question?
So the question is, what happens if I increase the temperature, right? What will happen? So if I increase the temperature, what will happen is that you will see this plateaus becomes narrower and narrower, and eventually will just recover this classical region. Yeah. So the other thing I would like to mention is this rho XX. So on the classical side, what I said, what I tried to say is that if you do the work more carefully, you will find rho XX to be the constant in the classical world. Depends on the scatterings of the electrons and so on. That's some intrinsic property of your material. But for quantum Hall effect, what you will find is that those rho XX stays exactly 0 at those plateaus. And it will only jumps as you change the from one plateau to the other plateau. So that is also observed experimentally. That is another property of those quantum Hall effect. Okay, so as I said, this course will I will try to explain how to understand those quantization of the quantum Hall of this Hall resistance, and it could indeed be summarized as two words. One is the so-called topology. That is, turns out that this quantization, this integer number nu, is related to some pretty deep mathematics that is called Chen number or Chen class in algebraic topology, which I will explain in the later part of the lectures. And the idea of topology actually becomes a very important and popular topic in nowadays study of quantum matter. So, and this really was started by in this quantum Hall effect. And another thing that is a little bit more surprising is that the disorder, or you can say the impurity, or the dirtiness of the materials plays a key role for these quantum Hall plateaus. that's really very counterintuitive compared to the things that we learned or we dealt with in physics, particularly theoretical physics, right? When you try to model some real system, the first thing that you would probably assume is that my system is clean, that there's no randomness, there's no impurities, and so on, right? But for this quantum Hall story, the thing is, those disorders or impurities is the factor that give rise to the plateaus of this Hall resistance. And without disorder, without impurity, you don't say plateau at all. That's really, that's really very surprising, and also a nice illustration that sometimes the dirtiness in nature can give rise to a very beautiful consequence in physics. Okay, so, and another thing that I would like to mention is that, so you can ask what will happen if I goes to a larger magnetic field, right? And then I won't have integer quantum Hall state, right? And it turns out that if you go to a larger magnetic field and also and meanwhile make the sample a little bit cleaner, what you will find is that the so-called fractional quantum Hall effect that I still get those quantized plateaus, but now those filling factors becomes fractions. For example, I can get 1/3 state, I can get the so-called 1/5 state, like 2/3, 2/5, 2/3, and so on, right? You can also get some filling factors that is larger than 1, and so on. You get a bunch of fractions. And most of those fractions actually has an odd denominator. And there are only a few have even denominators. And the fact that most those fractions have odd denominator is related to the fact that the underlying system is a fermionic system. It's a consequence of the fermionic statistics of my particles. Okay, and this fractional quantum Hall effect was originally discovered by those three gentlemen, Stormer and Gossard, in 1982, and after this remarkable experimental discovery, and Laughlin came up with a very beautiful way to understand, to explain those experiments 1 year later. And this, and no doubt that those guys also got a Nobel Prize at some point. And the remarkable, a new physics of this fractional quantum Hall effect compared to integer quantum Hall effect is that in those fractional quantum Hall effect, the system has the excitations that you can have in the system turns out to carry a fractional charge, not integer charge. And for this 1/3 state, the excitations that you can have in the system turns out to be 1/3 of the electric charge. And even more remarkable, those excitations have the so-called fractional statistics, right? In the morning, Nathan revealed the boson and fermions, right? And in the fractional quantum Hall state, those excitations are neither boson nor fermion, and this is what we usually nowadays called anyon, namely that if you consider two of such excitations, and you just exchange them, right? You will get a non-trivial phase factor, let's say EI theta. If theta equals to 0, we know that's a boson, right? if theta equals to pi, we know that's a fermion. And for anyons, it turns out that theta is neither 0 or pi, it's some fractional numbers. And for the 1/3 Laughlin state, I should specifically say that this is 1/3 Laughlin state. And for this 1/3 fractional quantum Hall state, this theta goes to 2 pi over 3. Right? And this is a so-called fractional statistics. And for each different fractional quantum Hall state, you will end up with different statistical angles. And sometimes things can even become more exotic, like you can get those so-called non-abelian anyons and so on, right? But this lectures will not really touch that. If I have time, I will, at the end of the lecture, I will explain a little bit about the physics of this fractional quantum Hall effect. The major part of this course is to understand the so-called integer quantum Hall effect. So, any questions?
You said that the excitations have fractional charge and anyons, not fermions or bosons. What do you mean exactly by excitations?
So the question was to what do I mean by exactly by the excitations? So what I mean is that when you try to perturb the system, right, the system will respond, right, and you can quantify the response by just thinking about you excite some particles in the system that move around. That is what we call excitation, right? And here, then you will find that the excitation will carry like 1/3 charge. Of course, the thing is the system is always built using electrons. So then that means if you really excite the system, what you will say is that you will let's say you inject 1 electrons in the system, right? And then you will say this 1 electron effectively gets split into 3 independent excitations, each carry 1/3 charge. They can move independently. That is what we call excitation. Yeah.
Similar to a hole in the. It's similar in modeling to a hole in the whole particle. Whole. Good afternoon. Whole, not whole inter, but that whole particle in the B semiconductor is similar to that.
Not sure if you ask.
The excitations, they are similar in spirit to the whole particle in the B conductors. That is, it does not really exist, but you model the system, the whole.
I think what you're trying to say is like the direct C was modeled like electron holes, so the hole moves like a particle. So that's
It's similar in concept.
Yeah, it's a little bit similar, right? The concept. So the concept of excitation is that it's a collective behavior of the electrons, right? Yeah, it's like a collective behavior coming from many electrons. They move together and so on. Then effectively, you can think it as some excitations in the system. Yeah.
Thank you very much.
So that is the basic experimental phenomenology of the integer quantum Hall effect, and as well as the fractional quantum Hall effect, right? And one thing you may say that is, okay, those are experimental phenomenon that has been observed for decades. So why do we still care, right? And indeed, there are many reasons for us to still it's still a very, very active research field right now. And there are many reasons that why we really want to care about those quantum Hall effect. So one thing is that it do have applications, pretty cool applications. Yeah, I should say potential applications. That is, you can make use of those fractional quantum Hall effect to make the so-called to do the so-called topological quantum computing, and the idea is that you make use of those so-called Anyang statistics that you can end up with quantum computing scheme that is error-free, right? You know, nowadays quantum computing becomes very popular subject. Many big companies have their own quantum computing devices, but all those devices suffers very large errors, which is very hard to really use it to apply to the problems that we are interested in. And the idea of those topological quantum computing is really a quantum computing scheme that is error-free, that there's no error at all in such quantum computers. And to build that, we want to make use of the so-called topology order or topology quantum field series. And fractional quantum Hall effect is really the most promising platform for realizing this topological quantum computing. And so I'm a theorist. So then for me, quantum Hall is really something that has a lot of fundamental importance. And very often that's the quantum Hall is a resource that we can get a lot of inspirations of various theoretical physics in different field. For example, what I have mentioned is that topology plays a very important role in the story of quantum Hall physics, right? And more generally, it's related to the so-called topological quantum field series. And in condensed matter literature is also called topological order that people have been studied for decades. And all those really started from this quantum Hall effect. And the quantum Hall effect also have deep connections with the conformal field series, which is another type of quantum field series that is closely related to many physical phenomena, like phase transitions like phase transitions in Ising model that Juan mentioned, talk about in the morning. And the other thing is the disorder in physics, as I explained, the disorder is really the key reason for you to get those plateaus of your Hall resistance. And the quantum Hall effect also have is also related to can also realize the so-called non-Fermi liquid, which is a very important type of quantum matter that also happens elsewhere, and is also has close relations with the, let's say, gauge series, and as well as something like dualities of gauge series that Nathan has mentioned in the morning in his class of supersymmetry. And there are also some other things. One thing is that get me excited recently is the so-called non-commutative geometry, which is also naturally appears in the in the quantum Hall context. So this list can actually be much longer, right? And I can spend a semester or a year to talk about the physics behind this quantum Hall physics, but I will not do that. But let me also mention one slogan about quantum Hall that I really like, is that it's like all in Hall, and that's literally true. Oh, no, it's just a slogan. Yeah, yeah. Some people wrote a paper with this title, but it's probably not. But it's not really what I want to say. So the point is that the physics behind quantum Hall effect is really very, very rich. Yeah, it connects almost every single things that we thought theoretically, and that's really give us a lot of inspirations about various physics, theoretical or even experimental physics that could happen in quantum matter as well as the high energy physics. Okay, so I think I'm done with the introductions, so I can pause a little bit for questions. So the plan of the rest of the lectures will try that I will first explain the physical mechanism behind this integer quantum Hall effect. If I have time, I will also talk a little bit about fractional quantum Hall effect. So are you asking the size of the Plateau? Is that? Yeah. It turns out to be controlled by the disorder strength. Yeah, the stronger the disorder is, the wider of the Plateau is. Of course, there's some cutoff that you cannot have disorder to be infinitely strong, right? I will explain this later in this talk, right? If you don't have disorder, then you don't have Plateau at all. One thing I didn't mention is that one thing you could notice that I draw it on purpose that each plateaus actually intersect with my classical trajectory of this Hall resistance, right? And then actually you can read out the rough value of the magnetic field. So the thing is, we should have this guy for certain magnetic field. We should have this classical resistance equals to my quantum Hall resistance, right? And then what you can get is the roughly nu, let me use approximate value, and then roughly this nu will equals to 2 pi h bar times n over E times B, right? And so if you want a very large nu, so this n is really the density of the charge carriers in my material. And then if you want a very large B, what you end up with is a very small magnetic field. And for that, it turns out that there are some other competing factors which may destroy the quantum Hall effect. So that's something I think I will explain when I talk about the physical mechanism for those integer quantum Hall effect. Yeah. Sorry again? That's a good question. So I will. Okay, the question is, does it depend on the spin of the charge carriers? So so we know in real materials, the charge carrier as always carries spin 1/2, right? And then you can ask whether this spins plays a role in the quantum Hall effect. So, so a naive answer is that when you apply a magnetic field, right, the spin get Zeeman energy, right? You do get splittings between the spin up and spin downs, right? And and then with some naive approximation, we can say that we can ignore the spin degree of freedom in the quantum Hall for those quantum Hall effect. But in reality, the story is much more complicated and also interesting if you consider the spin degree of freedom, right? So yeah. So any other questions? So if not, let's start encoding understanding the physics of the integer quantum Hall effect. And the most important thing to, the starting point is to try to understand just single particles, single electrons moving in the presence of a magnetic field. And that's probably some problem that you have dealt with or learned in quantum mechanics course, and that is called Landau levels. So again, so now we want to consider again just this electrons. Let's say we have a particle, which is an electron in my case, that carries charge minus E and with mass m, right? And it's moving in the presence of a B field. Yeah, I should not erase this. So I do have an electron, right, just moving in the presence of this B field, right? And now we want to deal with a quantum mechanical version of that, right? And the solution of this problem is called Landau levels. So I will do those explain those Landau levels and what's the physics of Landau levels for this and probably next lectures. And that's really the important starting point to understand both integer quantum Hall effect and fractional quantum Hall effect. Okay, so you probably know that the particles, the electrons, will couple with the magnetic field through the so-called minimal coupling. And what you need to do is that you need to introduce a vector potential that I will call the A, which this is a vector potential for the magnetic field, right? And then we know that you can write down the single particle Lagrangian for these electrons, which will be just my ordinary kinetic energy that I'm using X to represent the positions of my electrons, and X dot, and this is really just conventional kinetic energy. And I do have a minimal coupling that is my velocity of the system of the electrons is coupled to the vector potential, right? If that's the first time for you to say this, you can convince yourself by showing that from this Lagrangian. What you can do is that you can compute its equation of motion, right? And then you can show that the equation of motion of this Lagrangian give you exactly the Lorentz force. That's how you end up with this Lagrangian describing the electrons moving in a two-dimensional plane. Okay, so and with this Lagrangian, what we can do is that, for example, we can compute the canonical momentum that I will call P, and I should use, let me just use partial. We can define the canonical momentum, which turns out to be this, and I call it canonical momentum. And that's the observable that has this this relation, right? And one thing you can say is that this canonical momentum now becomes gauge non-invariant, right? Because it has this vector potential term. Okay, and I can define a mechanical momentum, right? The mechanical momentum is really, and then that is like this, and throughout this lecture, I will call it pi. And then with this Lagrangian, what I can do is that I can write down the Hamiltonian, right? And that's the Hamiltonian is what we want to deal with in this quantum mechanical problem. And you can write it as indeed as using the mechanical momentum, right? It's really just something we are familiar with, right? The energy is relative to momentum through this formula that we learned in high school, right? That is the Hamiltonian of this system, right? The Hamiltonian of two-dimensional electrons moving in the presence of a magnetic field. Okay, so now we want to solve this single particle problem to say what's its eigenstates and look like, and what does the eigenenergies look like. And its eigenstate is what we call Landau levels. Clear so far? All right, okay, the first thing that we can do, which turns out to be pretty simple, is just to compute the eigenenergies of this Hamiltonian, right? So we can, let me call it, and you will soon see that the eigenenergies of this Hamiltonian is actually quantized. So let's start with this canonical quantization, right? Now I'm putting indices into this commutators. This I and J are really just taking values between x and y, or 1, 2, if you prefer, right? And we also know that the coordinates as well as the momentum are commuting between themselves, right? That's basic quantum mechanics that we learned. So now what you know is that you can rewrite this canonical momentum just as the derivative of my coordinates. now what you can show is that now the mechanical momentum, right? The pi that I defined here will satisfy the commutation relation that is, so let me be more concrete. You just rewrite your mechanical momentum as P plus E, and you can show that this commutation relation to be minus EI times E H bar times magnetic field, right? So and then what you can do is you can define an operator that I called A, which is the I defined it as 1 over root of 2 E times H bar times the magnet B, and then I use the canonical mechanical momentum to define such operator, and naturally I will have a dagger to be similar to have a similar expression, but with a different sign for this due to the I'm conjugating I. So I define those operators, and the reason that I want to define those operators is that on the one hand, you can show that the commutation relation between A and A dagger now just becomes 1. Yeah, and that's the commutation relation of creation and annihilation operator that we also use to study the harmonic oscillator. Right, and more importantly, what we have is for the Hamiltonian, which is the square of the mechanical momentum with some 1 or 2 lines computation, you will realize that it's actually equals to H bar times E times B over M and times A dagger A plus 1/2. Right, that's really just an expression that we also encountered when you solve in the harmonic oscillator using those creation and annihilation operator. And now we immediately would know that what are the eigenenergies of this Hamiltonian, which will then be quantized, right? Just like a harmonic oscillator, right? And here I will define one quantity that is what we call cyclotron frequency. I will call it omega B, which is E times B over M, and it's called, let me also write it down, called cyclotron frequency. And that is an energy scale that we will enter many times when you want to consider quantum Hall physics and more generally the physics involving magnetic field and electrons. Okay, so we can solve this. So let me, as I said, it's immediately clear that the energy levels of this single particle Hamiltonian will be quantized. And we can write down its energy levels, right? Just like what we have for the harmonic oscillator, right? We can first start with the ground state that I call it 0, and it satisfies the relation that if I apply the annihilation operator, A to ground state, I will just get 0, right? That's just Okay, so that's just a harmonic oscillator, right? And then we can define the state that we can label at n. Don't confuse this n with the charge carrier that I also talked about. So if I can define this n state, and if I apply a creation operator on top of it to it, then I will increase this n by a number 1. And similarly, if I apply annihilation, I will get yeah, and you will know that the energies of those of each state will be this omega b is really just the cyclotron frequency, and it's h bar omega b times n plus 1/2, right? And this is what we called Landau levels energy, Landau levels, right? And that's how we get the eigenenergies of that Hamiltonian, right? And you can say that the derivation is really very straightforward. I would suggest you, if it's the first time for you to say this, I would suggest you to repeat the computations for both and also for what I would talk about later. It will be very helpful to understand this basic physics. Okay. So, but now you may realize that we actually miss one thing, right? So, so the problem that we start with is actually a two-dimensional problem, right? It has 2 degrees of freedom, x and y, for its position, right? But now I converted to some creation and annihilation operator, and then I end up just mapping it to the harmonic oscillator, which seems only have 1 degree of freedom. That is that is I denote as this n state. So it seems there's 1 degree of freedom missing, right? And the solution out of this contradiction is that actually for each for each Landau levels, it has a huge degeneracy, right? That's the other degree of freedom will correspond to. It may not be immediately clear that how to understand that degeneracy just using this second quantized language. So it will be helpful to understand that. We should to study this problem in a more tedious way. That is, we want to try to solve that Schrodinger equations corresponding to that Hamiltonian to get its wave functions, to have better physical understanding about the physics of Landau levels. So I can pause a little bit for questions. All right, so now let's think about the wave functions, right, of those states. So again, we want to solve that Hamiltonian that I wrote there. And as you know, first as you may know, the first thing that we need to do is that we need to choose a gauge, right? So I would first choose the so-called Landau gauge. Let me pronounce it. So remember that I do have my vector potential is defined in this way. So then what I can do is that I can choose a specific gauge that has that is what we usually call Landau gauges. So it's like the vector potential is 0 in the x direction, and it's non-zero only in the y direction, and the the value of this actually depends on x, right? So one thing you can immediately say is that this Landau gauge actually preserves the translation along let me say along the y direction, right? But it's break the translation in the x direction, right? That is the price we have to pay when we choose a concrete gauge. Okay, so now what we can do is that we just rewrite our Hamiltonian using this gauge, which is 1 over 2m and times my px square, and also because the vector potential I choose have the 0 component in x direction, and plus py time plus my gauge and square. Okay, that's the Hamiltonian we are going to we need to solve, right? We want to solve the Schrodinger equations, like that is we want to find state that is the eigenstate of my Hamiltonian, right? So the first thing that you should notice is that, as I said, this vector potential preserves translation along Ty, but breaks Tx, right? That also means this Hamiltonian preserves Tx, preserves Ty, but breaks Tx, right? That means there's a good quantum number that is a momentum along the y direction. So we can, so in other words, what you can show is that my Hamiltonian commutes with the momentum py, and then we can say py is a good quantum number, right? Py is a good quantum number for the state. Is a good quantum number for the state, which I will call it K. Okay, so now that means I can label each eigenstate with this quantum number K, and it will have this exponential IKY factor, just gives me the momentum of along this y direction, right? And then it will be some function that only depends on x, right? And it also depends on the momentum k, right? That's the wave function ansatz you can write down for this eigenproblem, right? And now what you can do is that now you just insert this wave function ansatz to this function equation, and then you end up with a differential equation, which actually, with no surprise that you will say, it's again reproduces the harmonic oscillator that we had when we think the problem in terms of the creation and annihilation operators. So, and you end up with, so you just apply this to psi k, you will end up with something like this, hk times psi k, and this hk is 2 pi m px squared plus 2 m omega b squared over 2 times x plus k times h bar over b, right? And that's what you end up with. And you may quickly recognize that that's actually the Hamiltonian for the harmonic oscillator, right? And then you can solve it and get these wave functions. I think I'm running out of time, right? Yeah, let me like maybe spend around 2 or 3 minutes to finish this. Yeah, so you end up with this harmonic oscillator, then you can solve its wave functions just like what you did for the harmonic oscillator, right? You can get this energy, which will be identical to this guy. So I will not write it down. And the wave functions, now we say it's clear that I get another label, right? That is n, which is really just the level of my harmonic oscillator. My wave functions will be like I get this exponential IKY. Let me call it H tilde. And that is the solution of the harmonic oscillator. That is Hermite polynomial that we learned in the quantum mechanical course. And that is my solution. And here LB is what we usually call magnetic length, which is really just this guy. It's another very important scale that, again, is called magnetic. It's another very important scale that would enters at many places in the physics of quantum Hall effect. So yeah, that's a H Hermite polynomial. Yeah, probably you are right. Yeah, yeah, that's something should be easily figured out in quantum mechanics. If you open a quantum mechanics textbook, then yeah. So the important thing is that here the eigenstates will have 2 labels. One is that I called n, which is just labels the state of this harmonic oscillator, right? And the other label is the momentum, that is the momentum along the y direction that I called k. And now you say that this momentum makes it different from the usual harmonic oscillator, and that's also the origin of this degeneracies of Landau levels, which I will explain in the next lecture. Okay, so I think it's good to stop here.
Yeah, so now we have time for questions. Maybe wait a little bit for the microphone. Yeah, you have to speak quite close to the microphone.
So it's just a quick question. Why couldn't we have 1K for y and 1K for x in the wave function?
Yeah, so the reason is because only Py is conserved, right? Px is not conserved, right? Because my gauge breaks the translation along the x direction, right?
I mean, but the momentum in the x direction must be the same of the y direction?
Yeah, that's a good question. So in the end, you can also choose another gauge. Let's say you just swap those 2 guys, right? Then you end up with wave functions that has momentum along x direction, but it doesn't have momentum along the y directions. it has to be break some way, right? And that, so in other words, those wave functions are not gauge invariant, right? Yeah. That is also something we learned in quantum mechanics, right? If you have magnetic field, then the wave functions may not be gauge invariant. So there's a question here.
Okay, 1 second.
I just want to know how you have there the presumption that the momentum in the y direction eigenstates are also eigenstates of energy. Can you, what in the problem gives you the, let's say, the hint that you can make this assumption?
Well, I think it's a basic principle of quantum mechanics, right? If some symmetries, if the Hamiltonian has some symmetries, then I can label the eigenstate of that Hamiltonian using the quantum numbers of that symmetry, right? And here, that is what I'm doing, right? I write down the Hamiltonian, and then I realize that it commutes with Py, that is a generator of the momentum along y directions. Then that means I can simultaneously diagonalize my Hamiltonian and the momentum operator, right? I end up with this ansatz, right?
Okay, understood. And then why can't you also assume it's an eigenstate in the x direction at the same time it is an eigenstate in the y direction?
Yeah, the thing is, this Hamiltonian does not commute with Px, right?
Oh.
So then I'm not allowed to do so.
Okay.
Yeah, it's all comes from the choice of my gauge. Yeah, I will also come back to this point about the choice of gauge. I will play with different gauge choice and then to give you an idea about what the wave functions look like.
Thank you very much.
More questions? One there. You can keep this microphone, perhaps pass it to someone.
Okay, how you can realize that in the quantization here in the first part, you can have the case for each n, I think, because here you have two quantum numbers, n and k, but here you only have just one.
Yeah. That's why that was what I said. If I formulate this problem using those correlation and annihilation operators, I miss some degree of freedom, right? It's kind of obvious if you just think it in a very simple way that my harmonic oscillator only have 1 degree of freedom, right? But the original problem has 2 degree of freedom, right? It's x and y, right? And then, so it's not totally obvious that how to get that degree of freedom back using this approach, although you can after you realize it's a momentum, right? And in this explicit formulation that I derive the wave functions of this problem, then it's very clear that the other degree of freedom that I have in the problem is a momentum along certain directions after I choose the gauge.
Okay. Also in this first part, it works for any gauge, no? For any gauge, I think, no? Because here you choose one.
Yeah, we choose one gauge. Right?
Okay.
So yeah. One thing I think I didn't mention is, which is actually obvious, is that at each Landau level, right, it's highly degenerate, right? And meaning that their energies are exactly the same, and I can have those momentum take different values. And then what you can do is that you just have use those wave functions to do some superpositions. You can get another basis of your eigenstate, right? And you can actually choose some way to superpose them such that those eigenstates have exact momentum along tx directions, but not have momentum along y directions. You can also do other more symmetric tries and so on.
My question is about fractional quantum Hall.
Yeah.
I know that when theta is equal to 0, it's a boson. And when theta is equal to P, it's a fermion. Well, what is a physical interpretation for a fractional value of theta?
Yeah, that is what we call the fractional statistics. And it's a phenomenon would only happen in 2+1 dimensions. +1 means the time dimensions. The thing is, the one way to say that why 2-dimensional is special is that, let's say, you can consider another process. I mean, it's the same process that I have 2 particles, right? I wind one around the other. That's really like exchange it twice, right? And now, in higher dimensions, what you can do is that you can just you can shrink this loop, right, into trivial, right? There's another dimension for you at disposal that you can just shrink it to identity, right? That means for this process, the phase factor I get will be identical to the to identity. That gives me EI2 theta equals to 1, right? That means theta equals 0 or pi. But in 2D, you are not allowed to do so, right? There's no extra dimension for you at disposal, and that means this kind of loop is different from this kind of loop, right? And it's related to the topology, right? People in math literature, that is called homotopy, right? Of this, and that means in 2D, then I can have a non-trivial loop, right? And then that means generically, I don't need this exponential I2 theta equal to 1. That's how we get, in principle, we can get fractional statistics. And it turns out that it happens in this quantum Hall systems, in the fractional quantum Hall systems,
In the solutions you found, it's not clear to me what values can K take. Are they real numbers, integers, natural?
Yeah, that's a very good question, and that's how you can understand the degeneracy of lambda levels, and I will talk about this in next lecture.
Okay.
More questions? Can you pass the microphone there?
Sorry, maybe I missed something, but how did you get to the final HQ, okay? The Hamiltonian with a...
You mean this one?
Yeah.
Yeah.
From what?
Yeah, the point is, it's a very simple thing, right? So what I said is Py is conserved, right?
Yeah.
It's a good quantum number, and then what you can do is that you just replace Py with K, then you end up with this.
Okay.
Yeah, but here I probably redefine the parameters a little bit and so on, right?
You didn't use the answers, right?
Yeah, we directly use that answers, right?
Okay.
Yeah.
Thanks.
So I find it a bit weird that physical observables should be independent of our gauge choice, right?
That's true.
So how can fixing the gauge differently lead to different conserved quantities?
Yeah, the wave function itself is not a physical observable, right? So then what we end up with is a highly degenerate states, right? And then you can use those degenerate states to superpose. You can superpose those degenerate states to get different bases. Like here, the basis I have have conserved momentum along k direction. Right? You can along y direction. You can also superpose them to bases that have momentum along x direction. I guess the solution. What I want to say is the solution is that you do have highly degenerate states. So then when you want to compute observables, then you should pay extra attention to those degenerate states. And after taking care of that, you will get gauge invariant observables.
Okay, so if there are no more questions, let's thank Yin-Che.